It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we are going to talk about the electromagnetic spectrum. So far in this unit we've learned about magnetism and the relationship between electricity. And we saw that a moving current will generate a magnetic field that's perpendicular to the direction of the current. And we also saw that moving a magnet down a coil of wire will induce current. Therefore, since that moving magnet down a coil of wire induces current, that moving current will also induce a magnetic field, and so on and so forth. That magnetic field will then induce current. One day, a scientist named James Maxwell realized the same exact thing. Maxwell stated that a moving magnetic field will induce a moving electric field, which will in turn induce a moving magnetic field. And these will continue to propagate each other. Continue to propagate. As long as they are moving at the same speed. Shortly after Maxwell came up with this idea, he decided to take a walk with his girlfriend on a nice romantic beach during a romantic evening. And while they were holding hands, Maxwell said, "Hey, why don't you take a look up at those stars and see how beautiful they look?" And as she looked up, he said, "How does it feel to be holding hands with the only person in the world of knowing what's created by the propagation of a moving magnetic and electric field?" She shortly let go of his hands and said, "How does it feel to be the only person to be dumped on a romantic evening like this?" and ran away. So during his silent time of pondering, he started talking to himself and whispering out loud, and he said that the propagation of a moving magnetic and electric field gives us the electromagnetic spectrum. AKA light. So the propagation of a moving magnetic and electric field is what creates light. Now we have an idea of light, that's things we see, and that's specifically visible lights. But if you look at our electromagnetic spectrum in our reference table, we could see that light consists of gamma rays, X-rays, ultraviolet rays, and then this tiny sliver of visible light. That's what we could see in the human eye. Infrared, microwave, TV, radio, AM, and long radio waves. So all these forms of waves we can call lights, but more specifically they are part of the electromagnetic spectrum. If you want to hear a little song in regards to the electromagnetic spectrum, you can click on the link in the description on the YouTube video. Now, we could draw a picture to represent the propagation of both the magnetic and electric field. To draw this, we're going to draw one axis going straight up, and then our other one is going to go slightly at an angle. And why don't we draw our electric field first? So we're going to draw a sine wave to represent our electric field. And what we're going to do next is draw arrows to represent the propagation of the electric field. And they're going to go straight up and straight down. Hopefully your picture looks a little bit better than mine. And the blue we'll label as our electric field. That moving electric field will induce a magnetic field. We'll draw another sine wave. And this time our magnetic field, we want it so it looks like it's going out of the page and into the page. According to Maxwell, this will propagate continuously. According to Maxwell, the ratio of the electric field over the magnetic field is equal to the speed of light, which is lowercase c. So c we can label as the speed of light. In a vacuum, the speed of light is constant. It's on the front page of our reference table, and it's 3.00 times 10 to the 8th meters per second. So what we could do is we can calculate the color of light if we're just given its wavelength. So why don't we do one example together? So in this problem, we'll be given the wavelength of a light wave to be 4.1 times 10 to the negative 7 meters. And we also know the speed of light, we'll say it's in air in a vacuum, is 3.00 times 10 to the 8th meters per second. Ultimately, what we want to determine is the color of light, of that light. If we look at our reference table, notice that the colors are dependent on the frequency of the light. So if we calculate the frequency, we can then calculate the color. So under the wave section, we use the formula V equals lambda F. And what we want to solve for is the frequency. So F is V over lambda, which gives us 3 times 10 to the 8th meters per second over the wavelength, 4.1 times 10 to the negative 7 meters. We plug that in our calculators and we get a frequency of 7.32 times 10 to the 14th hertz. So what we want to do next is look in our reference table, figure out where 7.32 times 10 to the 14th hertz is. In this case, it's in the violet section. So the color of light is violet. If we got the frequency to be something along the lines of 10 to the 16th hertz, we can look in our reference table, and 10 to the 16th is in the ultraviolet section. So even though we can't see ultraviolet, technically it's still a color, just invisible to the human eye. And that's it for this lesson. If you found it useful, please like and subscribe, and I'll see you next time. See ya.